I like to stick this in the front of my talks because it shows me pointing in my failed attempt to do interferometry with the two um, antennae pointed in behind each other like that, which obviously is incorrect. So there we are. Still nice picture. Righto. So but it shows my backyard anyway. Okay. Right. So this is hopefully this map has appeared now, just to confirm that everyone can see this map. Okay. Can you see a map on your screen now?
Yes, yes.
Yeah, yeah, brilliant. But by the way, I can hear you guys fine with the previous question. So just checking timing. We've got, I've got until 10 past 11 your time. Okay. All right. So this is where I'm located. So if you imagine where the UK is, this is pretty much smack bang in the middle, Birmingham, and we're located a bit north of it. Uh, we're sort of semi-rural here, but it is a massive populated area of about 10 million people around the sort of Birmingham area and around its surrounds. So certainly we get a reasonable amount of RFI and an awful lot of cloud and light pollution and everything that doesn't normally go with astronomy. But still, it's amazing what you can achieve wherever you're located. Always amazes me that. So the, I think what's changed in the last few years compared to previously is that it is now much cheaper to be able to get involved in radio astronomy, and there are a whole more bits of equipment that you can easily get hold of. And for me, starting off the Hydrogen Line program, I've become quite passionate about, was stimulated by SARA's Scope in the Box program, which is before I'd even heard of SARA. I actually found this online. And although I wasn't able to buy the $350 package, which initially I wanted, because I was outside the US, I was sent a list of components and was able to source all of those or versions of them on my local Amazon store. And I think that's made a big difference. I've got to say for you guys that I do think SARA produces some absolutely amazing manuals to describe to people how to do things in language which are can be understood by people without much of an engineering background. And congratulate you for that, because that's really quite an achievement. And so you might all know, so SARA's Scope in the package, sorry, recommends an aerial of this sort of type. The one that's there is a 2.4, unless it's been updated now, 2.4 gigahertz sort of Wi-Fi aerial. But this company, Neolec, in Canada, produced these various bits of equipment which have revolutionized amateur H-line work. And one of the things they produce is an actual tuned 1.4 gigahertz antenna. These cost now, a year or two ago, they were costing around about, I suppose about $200 would have been for you, £170 for us anyway, on our local Amazon store. But it's now come down to about £130. I think pounds are now running at about something like 1.2 pound to the dollar. It might be a bit cheaper for you guys there, being in North America. But for us still, nevertheless, to be able to pay for that relatively small amount of money, but off the shelf, a device that's actually tuned specifically for radio astronomy, I think has changed things quite radically. And the tripods, if you've never done this before, these are just standard tripods, which again are sold in places like Amazon and elsewhere. For putting satellites on, for portable satellite setups if you're going with your camper van somewhere. Here's a diagram which Alex put on the mailing list at some point, which is very helpful. Just include it, because if you're ever doing this project, one of the things you will wonder is where you actually put that post in the middle and which direction it goes in, because you can put it sort of north, south, or east, west. Just to show that it needs to go vertically compared to the long direction of the grid antenna, and that the grid antenna should then be orientated east-west And this is to do with something called drift scanning, where you point it in one direction, and as the Earth moves, the software then picks up for over a 24-hour period the whole sky at one particular elevation and translates all of that into a series of data which it can then process, which means you don't have to have any sort of fancy mount. Again, in case you do one of these, a different type of sort of ring feed here, just to show where that goes. Okay, so talking about fancy mounts or otherwise, this is what I use for mine. So this just requires a hammer, some nails, and no particular cleverness at all. In fact, I wouldn't even say this was done with any particular precision either. And that strange looking antenna on the upper right there is in fact an ex-military array, which so far most of my hydrogen line work has been done using. And as you can look at it carefully, you can see it's composed of a 4x4 set of dipoles at about the right frequency. And I can change the elevation, as you can see, using the battens on the sides. There's a series of holes. I've added some more holes in those since. And then you can just change how high it is. The reason I say it doesn't need to be accurate is because the software which I use, which I'll talk about in a minute or two, you just need to be able to tell it which direction it's aimed in. So a compass you need, and then you need to tell it what the elevation is, and you can get a very accurate account of the elevation using a digital inclinometer, which these days you can download for free onto your phone. So it doesn't really matter whether that gives you precise spaces between the holes or not, as long as it covers the actual series of elevations. And the other device which NanoVNA produced, which has made such a big difference, is this device called a Sawbird on the bottom left. In fact, on our screens, that's going to be so much bigger than the real device, which is only about the same size as that RTL-SDR.com dongle on the right-hand side. So it's just a small sort of finger-sized device. And this has a filter in it, which will filter out around plus or minus, I think it's 30 megahertz, around the 1420 megahertz hydrogen line, and will also two amplifiers, one after the other, which is the cascaded serial amplifiers, which will increase the gain of the signal, if I'm going to use correct terminology. And it only costs about 40 or 50 pounds. Now, I've added this in because anyone who's been following us on the SARA forum, or certainly who came to the last Drake's Lounge, will have seen me discussing the problems that I had with one of my hydrogen line telescopes, and the difficulty I had trying to sort it out until Jason helped me out here with told me to get one of these NanoVNAs, and then showed me how to use it. Not a device I would have said I would have been able to work out how to use without help, but once I've got it, it's just an amazing device, which is just absolutely incredible in terms of being able to both test whether stuff is working and also find out where issues are. And you can see here that I have actually a cavity filter made in China, and when you add that in, it dramatically narrows down the signal with the extra filtering effect. On the other hand, there's a reduction in the signal strength by about 3 decibels. So the question is, are you going to take the price of 3 decibels reduction, which is about 50% loss of signal, in order to get a narrower sort of signal bandwidth? In terms of what software I then use to collect my data, I started off using SDR Sharp and IF Average. I know there are many people in SARA who swear by this, and it's very good. It's what's recommended in the Scope in the Box package, or at least was when I got the Scope in the Box package anyway. And that little bump that you see between 1419 and 1400 and or 19.2 and 1419.6 on there, don't ask me why that's coming across as being a bit lower. I suppose it than 1420 is showing up on there. Anyway, that is the hydrogen line, which, as you noticed, is spread out, and that incorporates the Doppler shift, which gives you your information that tells you about different aspects of the Milky Way later on. Personally, I don't use that anymore. Or at least more accurately, I use it from time to time. But mostly I use Ted's here's Easy Radio Astronomy, which I just think is marvelous. And that's easily and freely downloadable off GitHub there. And it's composed of a number of Python scripts. So you just need to be able to learn how to launch a Python code. You don't need to be able to do any programming in Python. You just need to be able to learn how to launch it, and Ted will tell you how to do that. And then that will collect and process any data that you collect off your hydrogen line telescopes. And this is an example of data being collected using Easy Radio Astronomy. And again, I'll just point out, as I have on here on the diagram, that there is so hydrogen is 1420.405, and so we've got a peak that's around there, but it's spread out with some width, which is actually signal, some of it going a bit faster and some of it going a bit slower due to Doppler shift, and that affects the signal frequency. And this is the result of my first mapping exercise that I did with the Milky Way. And you can see that there's been a series of elevations which have been used on that wooden mount that you saw there, sticking that Ptarmigan military array, all pointed at 163 degrees south. You may wonder why 163 degrees south. That's because it is parallel to the slabs on our patio, and my wife prefers it. So that's the direction, simple as that. But it could be any direction. Most people would probably go directly south 180, but 163. But the software is more than capable of coping with that. And so you type that in, you type in the different elevations, which, as I say, I check with a digital inclinometer on the phone, and then each of those green lines represents a drift scan. So 24 hours would do it, but you can do it over several days if you want to, for convenience, and also to get a better signal to noise ratio if you wish, which is what I do these days. And there's the result of my first map, which, or more accurate, I think it's my second map actually. And you can see that the software has successfully shown both the Sagittarius arm and the Perseus arm. And if you look carefully with the eye of faith, you can see a number of other features which I've stuck arrows on as well. The background maps off Wikipedia for comparison. Yeah. This due to limitations both in the software and our position on Earth, it sort of limits what we can pick up to locally between 0 degrees, which is the horizontal line going left, and 90 degrees, which is the line going straight up. It's very difficult for us to be able to pick anything up between 90 and 180. Now, this is a modified picture which I've done, which I just thought is quite brilliant, because it conceptualizes this business of trying to pick up Doppler data. And certainly until I initially came across this, I found this a difficult concept to understand. So our sort of local standard of rest is where the sun is. So the sun is moving, but we're there. So as far as we're concerned, we're not moving. And then if you imagine different places around the Milky Way, which are represented here by different colored circles, which are going at different speeds. And the black line represents our telescope. It's looking out in a particular direction, and that's the direction it's looking at. And so it's looking out across the Milky Way, and at various points it comes across hydrogen, which is going in different directions and at different speeds. And you can see there that's represented, the different speeds, by the different colors and the different directions by the arrows. So speed plus direction equals velocity. So we say they got different velocity. But even if they're all going at exactly the same speed, those different directions, which you get simply from their location in the Milky Way, because the Milky Way is rotating, will mean that the amount of that velocity which is going in the direction of that arrow varies. So you will end up with a different as we measure it from the sun through our telescope. And what we end up with is what's on the right-hand side, which is our telescope's measurements. And you can see here, for example, that A and C look the same as far as the telescope is concerned, even though when you look on the graph, they are clearly going in different directions. Even though on the graph on the left-hand side, they're in a particular order, you might not have the same order as you get from the telescope on the right-hand side. So you need a bit of fancy footwork with your software to be able to turn that into back into the map on the left-hand side. Now, another thing I want to show you, just to come back to it, is the business of dark matter. Again, I just get this is off Wikipedia. I give it credit to Wikipedia. It's by Wikipedia Commons, but it's a really nice animation showing the difference between what you get if there is dark matter and without dark matter. So on the left-hand side, we imagine there's no dark matter in that particular galaxy. And on the right-hand side, we can imagine that there is dark matter around. So on the left-hand side, so I'm going to press the animation. And what you see is that on the left-hand side, the matter on the outside of the galaxy is moving much or rotating much more slowly than the matter on the inside of the galaxy. On the right-hand side, the matter in the outside of the galaxy is moving much faster, much closer to the same speed as the inside of the galaxy. And that's represented now by the graphs at the bottom. So you can see how it falls off on the left-hand side with distance and how it stays roughly the same with distance on the right-hand side. Just let it play out one more time so you can see that difference. Now here on the left, first of all, don't carry away with this. Start off on the left-hand side, the graph on the left-hand side. This is data that has come off Wikipedia. It's not my data. And this shows that same effect that you saw in the left-hand galaxy. The speed is dropping with distance away from the center of the galaxy, well, so in this case, the center of the solar system. It is, in fact, measurements of the planets in our solar system and their speed from the center. So you can see Mercury's moving much faster than Venus, than Mars, Jupiter, Uranus, Pluto, etc. On the right-hand side is actually data which was measured from my telescope. So this is my personal data, and you can see here it's much closer to a flat line. It may not be exactly a flat line, but what it definitely is not is what you're getting on the left-hand side. So it's not the Keplerian rotation of the left-hand side. It is something different. And the best explanation for that is that the presence of dark matter. Obviously, no one can see dark matter. So what we see is the smoking gun for it, which is that stuff isn't rotating at the right speed. According to Wikipedia, the sun's moving at about 200 and it's about 220 kilometers. Mine says it's about 243 kilometers a second. So it looks like mine's over measuring it, but we'll come back to that in a second. Because I found this data online when I was doing a bit looking up. This is published data, and looking at that graph on the left-hand side, to me, that looks much closer to the measurement that I've got than it does to the 210. So I'm beginning to wonder whether we're getting more accurate measurements than Wikipedia is stating. The other thing that you can do, and that Easy Rate Astronomy produces for you, is it'll weigh the Milky Way for you. So these are weights that the galactic mass that's come out of my measurements. Everything you'll have noticed in all these graphs is up to the distance of the sun away from the center, 8 kiloparsecs. We can't do much further out than that because our measurements at 8 kiloparsecs. Right. So having got all of that data, some time ago, Alex suggested that it might be possible to start plotting things from his H-Line 3D software in 3 dimensions, and came up with a piece of software called Rinnen 3D, which Ted and I looked at and to have a look whether we could find a way of plotting our easy radio astronomy data in that way. So I had then had to go using the H-line data that I had. And so here's some graphs that I have produced using that. And I think it's incredibly impressive that we're able as amateurs from equipment that's less than a meter in size to be able to produce three-dimensional plots in three spatial dimensions of the Milky Way. So this is showing that Sagittarius arm and a further arm further out. And you can see there that it sort of concentrates back down on the point at the top right, which is roughly where the sun is. And these are other graphs just from some different directions, the same thing where I've rotated it. I made a little animation of the same thing. Right. Easy radio astronomy has moved on since then and produced some other options. And in these plots, what's happened now is that the Milky Way data has been plotted onto a sphere. So this is looking at that sphere from outside. And you can see the Milky Way there going over the top on the left-hand side, and the other side of the Milky Way on the other side of the sphere on the right-hand side there. And this is now that same sphere, but from inside, from the center. So effectively, as if you were standing on the Earth, now looking up at the Milky Way going across the sky above you. Obviously, the picture's not quite as nice as you get from actually looking up at it from the Earth, but bear in mind it's being done with a radio telescope less than 1 meter. Further plots available is here's a relief plot showing the Milky Way data. In this case, the third dimension is actually power, and showing a couple of peaks. So again, Milky Way on both sides. This is from Ted's data at Little Thompson Observatory. Give him credit for that. Very nice plots. I hope he's putting it in my talk. And then there's some data from my own observatory. And this is over 3 days. And you can see the pattern repeats. See the drift scan is going over the same period of sky again. There's some different directions. And this is within a single day now, showing some detail with the single plot. With RIN and 3D, you can do various things, including filling the gaps in on the data, putting these contour lines on it to give you an idea of, or to amplify what the actual measurements are within the plot. Again, this is LRO data. And these, if anybody wants to have a go at themselves, this slide shows you the options that were chosen there for that particular plot. You can also flatten the image back out on that same RIN and 3D graph. Makes it a weird thing to want to do, but you then recreate the same sort of graphs that were being produced within easy radio astronomy. Some slight differences the way they look, and you might prefer this particular look. On the right-hand side, again, 3D graph from a different direction, this time flattened down. Now, moving on, we're now trying some different things at Lichfield Radio Astronomy. So there's the ptarmigan up the top left-hand side there. I've now got, Alex has made me one of his patch Yagi, 13-element patch Yagi, which I'm trying to get working. I've had great difficulty getting it to work, but embarrassingly, we've come up with a suggestion why it might not be working. And it might be that, in fact, to do with the mount that I've got it on being metal. I don't know whether that's affecting it or not. So I'm going to try a different mount on it, but I'm also going to use a NanoVNA to actually test the components and see whether they are properly functioning. But this should have the advantage of, say, being small, efficient, easy to put together. I know that Alex is very keen to allow them to be used by anybody with very little experience and easily transportable, and students, etc. The other thing is that I've acquired one of these. So this is a 1.5 meter parabolic dish. These are sold on eBay for only about $50 as solar cookers. So you put your kettle in at the focus point and it boils it away at a couple of thousand watts. I put this together when my wife wasn't looking, put it out in the garden, and then it has a reflective surface on the top, which is a bit of mylar reflective film. And when I sort of found my leg bird and then held a cardboard box to its focal point and it burnt a nice hole through it, I realized I had to do something about the mylar film. So I've spray painted that over now. And I was having great difficulty getting it to work. So with Jason's help here, we got the NanoVNA and tested the components. I was using as a waveguide, or still use a waveguide, this antenna which I'd made using some SARA instructions. I hadn't really known what I was doing when I did it, so I thought maybe that might be the problem, but in fact that's performing quite well, so that wasn't the issue. So that's the waveguide again, which is made as an old coffee tin plus a straightened paper clip with just the connector, the chassis connector at the side. But what we discovered was the problem was that I hadn't realized there were two different types of SMA connectors on the end of my coax cable. I had one of these reverse polarity SMAs on it. So if you imagine a male reverse polarity SMA on the end of the coax, and then so the other way around, sorry, it was a female. Sorry, we got on. Whatever. Trying to work it out. So yeah, sorry, that's right. The female SMA, I think it was on the end of the new Thornett, and a male reverse polarity SMA on the end of the coax. So there was no actual central connector connecting the two together. And as a result of that, it was getting minus 32 decibels attenuation across the cable. And as soon as we put an adapter in between the two, it shot up to -2. And now, lo and behold, I'm now collecting hydrogen data from it immediately. Sometimes it's amazing how the most silly things can cause problems with this type of project. So there we are. There's a picture showing the hydrogen data being collected. And we've now got a very nice peak, 1,420. And just I thought a little animation to show it coming in. If anyone's not seen hydrogen being collected over a 24-hour period. It's hitting the Milky Way now, and then coming back out the other end. Okay, just to show this was even, by the way, even with that RP connector to the SMA, somehow that solar cooker parabolic thing was still collecting some hydrogen. And here we are, just showing I was able to measure the Milky Way in spite of 32 decibels data loss. Weird. And there we are. Thank you very much indeed.
Questions? I have a question. Andrew, would EZRA work on frequencies other than those around the hydrogen alpha line?
I think I'll pass that over to Ted to answer that question.
You can change the frequency of the reference. You can change the frequency of what's called the antenna, the signal we normally care about. I don't know what's going to make sense. It's kind of customized to notice the difference between those two so that you can highlight hydrogen. But give it a try. It certainly can record all that stuff.
Did that answer it, Kurt? What I'm actually curious about, Ted, is if you want to take, so I usually look at the channel 37, so the 608 to 614 megahertz. Could I use EZRA for that? I realize we're not looking at hydrogen alpha. And I'm
When I
using-
don't have an antenna, I just put it on the FM broadcast band, and sure enough, I see things. I'm not sure it makes much sense because I'm really not decoding anything, but in theory, it will record the power available, at least in a relative way. What is the power compared to the other power you're measuring? That kind of relativeness.
Yeah, well, I'm only using it as a total power, but I'll just give it a try. Thanks.
I personally have used it mostly for characterizing my beam using the sun as a test source.
Yeah.
And I'm looking at the hydrogen band, but in that case, it's a total power thing. So I set the reference frequency to 0, and I just look at total power. So I would imagine that you could do the same thing at any other frequency, and you would still get a 2-column. Well, you'd still get a data file with frequencies versus amplitude levels, and then you could dump that into whatever you want to do your post-processing. So, now, all of his post-processing stuff is customized for mapping the Milky Way,
Right.
but the data collection is just straight data collection, so you can do whatever you want to. Correct me if I'm wrong, Ted, but I think the collection utility is pretty much just raw data, so you can do whatever you want with it.
Correct. It's just writing down numbers. You get to pick some frequencies, and it might shift back and forth as you wish. The post-processing is very flexible, and so you can use it to some effect for many other purposes. Good luck. Give it a try.
Yeah, that's what I was particularly fascinated by, was the post-processing aspect. So yeah, I'll give it a shot.
Well, thanks, Andrew. Appreciate it.
Yeah, well, thank you very
Um,
much. Yeah. Can I
can
just say that each time I usually give this talk, initially I thought, oh gosh, everybody on SARA is experts at these things, and I'm just teaching everybody to suck eggs. But normally somebody contacts me and asks some further information, and usually says something along the lines of, I've been doing this stuff for years, and I've always wanted to do hydrogen line work, but never got started. So what I say is, if anybody does want to speak to me, and then just talk through at a basic level how to do hydrogen line. I say basic because that's all I'm capable of speaking about. But then if you do, please just go onto my website, which is astronomy.me.uk, and there's a contact page on that, and just drop me a line. Thanks very much.
Right, thanks.
So,